So in the last few minutes, or how much I have left here, I'm going to try and tell you about why some of the most recent or current studies that we're doing right now on these supermassive black holes in these early type galaxies. And first I want to tell you that, as you probably already sort of guessed, that we don't have too many quasars in our backyard. So they tend to be more common at earlier times. So what this is really showing is just if this is birth of the universe and this is us now. So this is just telling us that half the age of the universe is here. So we're looking back in time as we go to larger and larger distances. And this actually shows that quasars were most, this is just numbers as a function of, you know, numbers in the volume. So it just shows that there's most of the quasars were really most prominent in terms of numbers when the universe was only about 10 to 30% of the age that it is now. It's a long time ago. And right now, in comparison, we almost see no quasars. We still have a few in our backyard, but thankfully not too close. What's that? Oh. Okay. So if you actually go out and measure the mass you can measure the mass by looking at the velocities of this gas. You can actually measure the distance to that gas by looking at how long it takes for a burst of continuum emission to reach that red line emission gas. Because there will be a delay in the burst of the continuum emission. First you see the burst of the continuum, and then you'll see, a time later, you'll see that line gas actually respond. So you can measure the time travel time of the photons, and that tells us, when we know how fast light travels, tells us how far away that gas is from the inner part of the accretion disk. And using that, we can determine the black hole masses. And what this is showing is, I put redshift down for you, those of you who actually want to see what redshift is, but I have the age of the universe down here. So you have sort of a guess of, this is when the universe was only a 14th of what it is today. What this shows is the black hole mass, and this is actually showing, this is a million, this is 100 million, and this is 10 billion. There you go. And in the local universe, you can actually get down to about 1 million solar masses, which is where our own little galaxy is. Yes, a wimpy, I'm sorry, it's a wimpy black hole, what we have in our local galaxy. But when we go to higher distances, further out in the universe, when the universe was younger, these quasars are really, really massive. 1 billion solar masses, 10 billion solar masses. And even out at the earliest time that we see these, where this is where most of the quasars actually are most numerous. This is out here. You see, even beyond that, when we're at this very drop-off, they're very massive. The ones we can see are very massive. Now, the fact that we don't have any objects down here is just not because they're not there. It's just that our studies or our surveys cannot go faint enough to see them. But we do tend to see that there is sort of an upper limit around 10 billion solar masses. And if we are to actually go on and look at larger surveys, it just shows more data, it kind of shows the same thing, that there seems to be sort of an upper limit around 10 billion solar masses. And that's when these black holes stop growing and turn off, because they obviously don't tend to grow more massive. Even at the highest redshift, they're really, really massive. Now, one of the questions is we know that these sources have to sit in galaxies. So if we are to look at galaxies or quasars that look out at when the universe was only 1.6 billion years old, so it's about 1/7 of what it is today, what do the galaxies actually look like? We have these very, very massive black holes, so they tend to be very mature. We have a very, very powerful quasar, but has the universe actually been able to make galaxies that look just like the galaxies we see in our own universe? Basically, if you were to sort of make a sort of little timeline between the black hole, I'm a little biased, aren't I? The Big Bang, and going out to, as the universe is cooling, all the gas is cooling, at some point we get to the dark ages where all the gas is cooling, there's no stars, there's no galaxies, they have to condense out of that gas. And it's only some time later that we get the first stars and the first black holes, and that later form into galaxies. And right now, we can only measure with the Hubble Space Telescope out to a redshift or a distance that's sort of around here. Okay, So as you can see, we can't really probe very far back in time relative to the whole timeline of the age of the universe. But still, we can do that. Now, one of the things that astronomers have been thinking about is exactly how do galaxies form. So usually we think of it as, okay, you have gas that collides, or actually collapses into you know, something that's denser when it cools from the early universe, and then it just grows bigger and bigger and bigger, because every cloud of gas has a certain mass and has a gravitational field, so it will attract more matter, and it will just slowly grow and form stars, and then those stars kind of get older, and then you have an elliptical galaxy. Now, the big question is, when do the black holes really form, and where do they actually start coming into this picture? So some people have been thinking, okay, well, you can just kind of add at some point in the very center, this center gets very dense and it can form a black hole, and then that black hole just kind of grows bigger, and then once the galaxy is fully formed, it grows big enough that it can turn on as a quasar, and then when that quasar just fades away, you have an elliptical galaxy with a black hole in the center. However, it could also be another way. What if these black holes form first? I know it's kind of a scary thought, isn't it? Okay, so the thinking is, you have the first cloud of gas that maybe forms the first stars, and if it's big enough, it can actually form into, through the star formation, it can actually collapse into a black hole. Okay, so what if you have all sorts of different clouds like that that have tiny little black holes that merge with it, and then it grows? Grows by accreting matter, but it also grows because you have two black holes merging. Okay, cool. And then at some point you have a galaxy where you have the black hole there that's quite big, and then the star formation starts turning on in this galaxy because the gas in the galaxy can start cool enough to actually form stars. So that means you can actually have a quasar at the same time when you have a lot of star formation going on. You're actually building up the galaxy at that point. So that's the idea. Oops. Okay, so you end up having a galaxy that at that point have lots of blue stars, and it's forming the most of the galaxy at that point. And then as it fades, you have both the quasar and the black hole fading as well as the galaxy, and you have an elliptical galaxy with a big black hole in the middle. So those are different ways of thinking of it. So the whole thing goes, of course, back to, okay, can we actually study these sources well enough? And this is a study actually using the Hubble Space Telescope out at a distance where the universe was only 1.6 years old, so that means 1.6 billion years old. That's about that part of the diagram I sort of highlighted with the red color. And one of the things that we see when we subtract that very bright nucleus, or the very bright light from our images of these sources, is that there's lots of fuss. We see the galaxy, but we also see little galaxies that are at the same distance. So it's very likely that these little tails and whatnot is part of the buildup of the galaxy. The fact that smaller parts of, or smaller galaxies are actually falling into this very big center. You can see most of them have sort of structure and smaller components. This is a galaxy or a quasar where it's so compact we can't actually resolve it at all. The galaxy itself is so small that it hides underneath that nuclear part of that we have to subtract. Okay, so the question is here, are we looking at galaxies that are caught in the act of building up most of the galaxy, or could this just, what we're looking at, could that just be the last sprinkle of fireworks? Because what we're actually looking at, I forgot to tell you that, the light we're looking at is very ultraviolet in the rest frame of these quasars. So it shows us where all the young stars are. So we're seeing lots of young stars that are forming a rate of 1,000 solar masses a year, so about 1,000 suns per year. So the big question is it actually building the galaxy at this point, or is it just the end stages of a long process of building up the galaxy? And of course, you already know all this because I already told you, right? Because you can actually look at the stellar ages, and that would give it away. So the big question is, okay, how many blue stars relative to the red stars are we seeing? If there is only a little bit of red, a little bit of blue stars relative to a lot of red, we're probably in this category. But if we see a lot of blue stars and less red stars, probably tells us something about the fact that this is a very young galaxy. It's in the process of being built up. So in order to actually study this further, we actually need to go out to, let's have this, we've kind of been here before, right? And we need to go actually further out. HST is the Hubble Space Telescope, can take us that far. We need to go out here to actually figure out what's going on. This is the first stars and the first black holes. So we need to kind of go out there. And we need to wait for a new telescope that's coming online in, well, they just postponed the launch of it to 2019, I believe. But it has a sensitivity way out in the infrared, where it's really sensitive to galaxies and stars that are so far away that the light is shifted all the way into that part of the spectrum. So we have to wait. But one of the things that we can do is actually go in and look at some of the most distant quasars that we know. And some of the interesting things that we're seeing is, this is actually just showing some data, that some radio data, that shows us that lots and lots of molecular gas out there. So these are the images, and these are some spectra that shows the velocity of that gas. But basically all you need to take away from this is that what we're measuring is lots and lots of gas. There's lots of fuel to form stars. So this shows that these quasars in their galaxy system have lots of fuels to build up a whole galaxy. And so the big question is exactly, is that actually going to turn into stars? Or does it already have a lot of stars? And this is just, some remains of it that maybe we won't even use. So that's a big question, but it looks very promising. Another really interesting thing is that if you look at those most distant quasars that really sit in baby galaxies, this is where the baby galaxy part comes in. What we're seeing is that if we measure the black hole mass of these, so this is what we're seeing down here, and we're looking at how much warm dust there is in these sources. Whenever you have star formation going on, these stars will form lots of dust. And when the galaxy or the quasar shines on them, or the quasar light shines on them, it would heat up. And so the more gas there is, and the more photons or light that can actually shine on them and heat them up, the more infrared light you'll see. You probably know about infrared light as being this heat radiation you can see in like night goggles and stuff like that, right? So this is exactly what we're looking at. We're looking at the heat from dust out of these very, very distant galaxies. And what we're finding is that if we look at how much heat we get from the dust, it's correlating with the black hole mass. And you're probably going, okay, so what does that really mean? Well, we think it may actually indicate that the quasars that have very small black hole masses also don't have a lot of dust, while the ones that have larger black hole masses have a lot more dust. It could show that what we're looking at here are some really tiny baby galaxies, the ones where the quasar, the black hole itself, is not very massive, and the galaxy itself hasn't actually formed that many stars because it hasn't formed enough dust to be heated very close to the black hole. Yet the ones that are more massive have lots of dust. Of course, we don't know for sure, and we need to take more data and study this further in different wavebands as well. But so far, it's actually kind of exciting, because we're wondering if we might have finally cornered some quasars that actually look to be infant. Maybe these are the first quasars that are building up the stars and the dust in the galaxy. And if we were to find some more of those, maybe that could tell us something about how galaxies are forming and how the black hole in the center could actually affect the evolution and the formation of these systems.